Okay, so welcome back. So last time we discussed that if you have the ring of integer OD of the quadratic field Q root D, then every non-zero prime ideal is maximal. And the way we proved it actually, that you take any non-zero ideal I, then OD mod that I is actually a finite abelian group, let's say. So that means, in particular, if it's an integral domain, if P is a prime ideal, it's an integral domain, then OD mod P is a finite integral domain, so it's a field. So it's a maximal ideal. Because OD mod I for any non-zero is finite, this index we define to be equal to norm of an ideal. And indeed, then I gave this exercise that if you take an element alpha, that's an algebraic integer, then this definition of ideal, principal ideal generated by alpha is essentially the same as the norm of the element alpha. And also, if you think the determinant definition of norm, that multiplication by alpha from Q root B to Q root B is a linear transformation, so that is a matrix. And determinant of that is the norm. Indeed, the characteristic polynomial, the constant term, the minimal in some sense is the norm. So the determinant, this determinant definition is same as norm and is essentially same as the norm of alpha. So all the definitions, all three actually, all three, I should say, all three definitions of norm agree. And I made a side remark that so if alpha is an algebraic number, then there exists n such that n times alpha is an algebraic integer. And if you prove that set of algebraic integer is a ring, then it will follow that set of algebraic numbers is a field, and from there you'll be able to prove that the Q bar, the algebraic closure of Q, is field of algebraic numbers. And then I worked out this example that Z root 2 is a PID, so this gives an example of real quadratic field, which is a PID. So next we want to prove this important result, and we'll see various applications of this. But before that, I want to make another side remark that more generally one can show. So more generally, that theorem, and this I stay without proof as a fact. And you can take this as an exercise, or slightly tricky exercise, that alpha in C is an algebraic integer if and only if Z alpha, so this is alpha. Okay, so maybe I can write here, if and only down. If and only this is the ring, the abelian group of the ring this is a subring of C, if you like, is a finitely generated abelian group. Okay, if and only. So if you find an algebraic, if you find a complex number such that Z alpha so the ring generated by F alpha or Fx is Zx is the abelian group of that is a finitely generated, then alpha is an algebraic integer, and on the other hand, if alpha is an algebraic integer, then the abelian group of Z alpha is a finite integer. So it is easy to see. Excuse me. It is easy to see. So, so recall that for alpha belongs to OD, Z alpha is Z alpha is so alpha Z alpha is a finitely generated is generated by the abelian group generated by at most two elements. Okay, for example, alpha might also belongs to Z, then Z alpha is nothing but Z. But so then it is generated by one element, but in the general case also it is generated by at most two elements. Okay, so you try to convince yourself that this is the case. Okay, so more general this is true. So if you're interested, and using that, one can prove that set of all algebraic integers forms a ring, and if you prove set of all algebraic integers forms a ring, then you can prove that set of all algebraic numbers forms a field, and there you can reduce Q bar is set of algebraic the algebraic closure of Q is this field of algebraic numbers. Okay, so uh, uh, so so now let us prove an important theorem that alpha be a non-zero ideal. Then there exists uh, so let alpha so now this is a new important topic we want to discuss. So if I is a non-zero ideal in O, then there exists a non-zero ideal J in O. It's OD, principal ideal in everything is happening in OD. Okay, so proof. So in fact, the idea proving this, you consider I and you take I bar, which is defined to be equal to sigma of I, then this is equal to norm. Okay, this is the idea of intuition. Okay. So formally, so you define sigma of I to be equal to sigma alpha, where alpha belongs to I. Okay. So first of all, let's check that this is okay. So this is idea, but this is the proof. So I so let I be an ideal in OD, and you define sigma I to be sigma alpha alpha belongs to I. So check that this is an ideal in OK, or in OD, and this is because alpha belongs to OD. Then so first of all, sigma alpha belongs to OD, or alpha belongs to OD, and so I mean sigma of OD can check to be equal to OD, and so then if you have R dots sigma alpha, then we can write it sigma r prime, sigma alpha, sigma alpha belongs to sigma I, for all alpha belongs to I and R belongs to OD. So this implies that sigma of I. So using that, one can check sigma I is an ideal OD. Okay. So you can check. So using these and check that. So using this can check that. Uh, so mm, what observe that one. So first of all, so you define this as an ideal, and now you consider this ideal I into sigma I. Okay, so this is also sometimes it's denoted by I bar. So this is recall the summation alpha beta alpha I beta I alpha j beta j j equal to 1 to n alpha j comma beta j alpha j belong, or I can write the sum of alpha j and sigma beta j alpha j comma beta j belongs to I. This is the definition of product of I times sigma I. Okay. So uh, mm, finite sum and n varies, right? N belongs to n varies. In particular, alpha times norm of alpha belongs to I times sigma I. Sorry, alpha times sigma of alpha. Norm of alpha, alpha times sigma of alpha, right? This belongs to I times sigma I for all alpha. Alpha belongs to I, right? And where are these? And also recall norm alpha belongs to Z, so all alpha belongs to, right? Because I is a subset of OT. And for all algebraic integer, the norm is integer. So let I equal to the ideal generated by norm alpha belongs to I. It will remain J is the ideal generated by these elements. So ideal generated by this in Z. Okay. So norm alpha belongs to I. These are elements of Z, and so you have this subset of Z, and you look at the ideal generated by this inside Z. Given any set, we can consider the ideal generated by this in Z. So this is equal to M times Z. Okay. So now my claim is I times sigma I equal to M times O OD equal to the ideal generated. Okay. So this is the claim. Okay, so this is equal to M, and this is in Z, this is in OD, this is in OD, and on the other hand, this is happening in Z, this is happening in OD. So the definition is that, let me repeat, you take the collection of alpha, alpha belongs to L, This is the ideal generated by collection of norm alpha inside. Okay, so you collect all the norm alpha. These are elements of Z. You just collect all of them. So in some sense, this is the GCD. Okay, this is like the GCD. This is like GCD inside, whatever that means. Okay, this M. Okay, right. So anyway, so there is a PID. So the ideal generated by these elements will be a principal ideal, and it will be non-zero because alpha is at least one non-zero element. So call that the smallest positive integer. This is the smallest positive norm in alpha in some sense. Okay. So I am claiming alpha times sigma is this. So first of all, I have to show MOD sum of I times sigma I, and that is easy because m equal to, since m is generated by this, m equal to summation sum lambda I times norm of alpha I equal to sum 1 to r, and this alpha I belongs to I and lambda I belongs to z. So by definition, all these elements are, so this implies m belongs to I times sigma I by definition, because all this norm I, these elements are inside I times sigma I. So m is also in I times sigma I. So this implies m times OD is trivially inside I times sigma. Now the other way, okay? Now you take the other way, so you have to show that um, so so this is okay. Then now second is I times sigma I is contained inside m of O. So again, this is, as you look at this, is generated by alpha times sigma of beta, this kind of thing. So you call alpha, so let's call it alpha beta, let's say alpha of sigma beta, where beta is in beta belongs to sigma I. Sorry, alpha beta belongs to I. If I can show, so suffices to show that belongs to M OD, so all alpha beta belongs to, right? So because if it is diagonal alpha times sigma alpha, then obviously it belongs to M, because it is the ideal, it's a Z multiple of that. So in particular, it's OD multiple of that, but we have to show this. So now you observe that, now the small trick, observe that what is norm of alpha plus beta minus norm alpha into norm minus norm beta. Okay, and this is equal to uh, so alpha, so this is alpha alpha sigma beta plus sigma alpha into beta. Right? Everything is commutative, there is no worry. So this is nothing but this is equal to trace of alpha, the sigma square is identity alpha sigma beta, right? And alpha and sigma beta are algebraic integers, so this belongs to Z. Okay, and you look at norm of alpha and sigma beta. So this is equal to norm of alpha into norm of beta. So this also belongs to Z, right? And so it and norm of alpha times sigma beta uh, is in fact, so this is divisible by, this is divisible by m in Z, and this is divisible by m in Z, right? Because, so what was this? So you look at the definition. This was the ideal generated by this, right? So all these element belongs to this ideal. What is the this is the ideal gen by M. So every element here looks like a multiple of M. So M divides all of these elements in alpha, right? This is the ideal gen by all these n alpha, and this ideal is M. So every n alpha is a multiple of M. So so this is divisible by M, and this is divisible by M, and this is divisible by uh, similarly this is divisible by M, because this is divisible by M, because this is divisible by M, this is divisible by M, this is divisible by M. Okay, maybe I should say it here. Then this is um, is all of these are divisible by M, right? So and so this belongs to MZ, and this belongs to M square Z. And why is that? As I explained, the norm of alpha plus beta is an element of this ideal generated by M here. So it belongs to M square Z. These are elements generated by M. Yeah, because this is the ideal. So this is, as I said, the way to think it is the GCD. So all these elements are divisible by M. So now any algebraic integer. So here, so trace of this algebraic integer. So alpha, sigma, beta satisfies the monic polynomial x square minus trace of alpha sigma beta into x plus norm of alpha sigma beta equal to 0 over z. Okay. Now you put it, so x square minus some a times mx plus bm square equal to 0. And a comma b belongs to 0. Because of this is m square, this is m, multiple of m. So this is multiple of m, this is multiple of m squared. So we can give it a name. We call this 1, this called 2. So by 1, 2, right? So that means that you look at alpha, sigma, beta, uh, by m squared minus a times alpha, sigma, beta by m plus b equal to 0. And a b belongs to 0. Right? Just look at this alpha, sigma, beta satisfies this. So you divide by m squared, this is what you get. So that means that this is an, you put this gamma, putting gamma equal to alpha, sorry, oh, alpha times sigma beta. You put gamma equal to alpha times sigma beta by m, then gamma square minus a gamma plus b equal to 0. At ADR in Z, this implies that alpha sigma beta by m belongs to OD. It's an algebraic integer inside Q root D. So this implies that alpha sigma beta belongs to M OD for all alpha beta I. So this implies I sigma I OD. This was the part 2, right? Alpha I sigma is in MOD, and it has suffices to show alpha sigma beta belongs to MOD for all alpha beta. That's exactly what we right? Because this is an algebraic integer, this has to belong to OD. Everything is happening inside QBP. So, uh, and of course, gamma, this belongs to Q root P. And okay. So we have shown, so thus we have shown, so thus we have shown I times sigma I equal to m times where equal to m times OD, where m equal to the sort of GCD of all norms of norms of all the elements of all the elements of I in Z equal to actually the ideal limit by norm of alpha belongs to precisely this in Z ideal in Z. So exercise is actually so for every ideal I, so for every ideal I, uh, okay, non-zero ideal, there exists J ideal, okay, such that I times J equal to M or some M equals to, okay, that is again non-zero. So M is of course also non-zero. And then the exercise is actually exercise. This M is nothing but I times sigma I equal to norm of I, the ideal length by this. So this M is nothing but the ideal norm. So we have defined the norm of an ideal, and this M will turn out to be nothing but norm of this ideal. Okay, and the second exercise is norm of I into norm of J, norm of IJ, I comma J are non-zero ideas in OD. Okay, so now we'll be able to show this thing also. So we showed that yeah, so we showed that for every non-zero ideal, there exists an ideal J, so that I times J is the principal ideal. In fact, that J is the sort of I bar or the conjugate of I. You take conjugate of all elements in I. That's for my ideal. And I times sigma I, we are able to show that we take the norm of every element and that generates an these are integers because we are inside algebraic integers. So you take the ideal gens by those elements as a principal ideal that is generator. And in some sense, there's the GCD and PID the GCD. Uh, so, so, mm, so it's the GCD of the norms of the element generated by that. And now you'll wonder, there is another integer, namely norm of the ideal, which is the index of the Abelian group I inside OK, which is a finite index. And you consider the ideal gen that. In fact, this will be equal to this. It requires some work, but you can think about showing me. And also you can show norm of I into norm of J equal to norm of I. So let me tell you this couple of steps, what was the main idea here. One side was easy, that this M is contained inside the product of the ideals. And the other part is that the definition of I times J is, so here the choice of J we made um, and define the choice of J we made is sigma I. So all sigma alpha, where alpha is an I, that's easily an ideal. And we wanted to show I times this ideal is equal to, so we did not quite show norm, it's GCD of the norm elements. And that I times that ideal is principal. And so this consists of element of the finite sum of element, product of two ideals is product of some finite sum of products from the elements of the two ideals. So this is of the form alpha j and sigma of beta j, or alpha j beta j are in I. In particular, for beta j alpha j, the diagonal elements are norm of alpha. But other than that, every element looks like some alpha times sigma of beta. And you have to show that alpha times sigma of beta is contained inside M. So the trick we did, that alpha times sigma of beta, the trace is in M times Z, and norm of that is in M squared times Z. So any algebraic integer satisfies x square minus trace into x plus norm of that algebraic integer equal to 0. So we wrote down that equation. Because it's of the form am and bm square, then for this algebraic integer alpha times sigma of beta, it turns out alpha times sigma of beta divided by m is also an algebraic integer. And of course, it is in q root d, so it is in OD. So that means alpha times sigma of beta divided by m is an algebraic integer. So alpha times sigma of beta is a multiple of m inside OD. So it is I times sigma I. All such alpha beta it is true. So finite sum it is true. So I times sigma I is contained inside OD. The other part was easy, so that was the equality. Okay, so with this now we can do a very important thing. So we know that for any ideal I, there is an ideal J. So now you consider, okay, so you consider with this ingredient, now you consider, so consider the set of uh, non-zero ideals of OD. Okay. So on this set, define relation uh, I is related to J if and only if there exists alpha beta belongs to OD, alpha beta not equal to 0, alpha is not equal to 0, beta is not equal to 0, such that alpha times I equal to beta times Q. Okay. So you consider the set of non-zero ideals and you define a relation that I is equivalent to J if and only if there is two ideals, two elements alpha and beta in OD, alpha, beta, alpha not equal to 0, beta not equal to 0. So the alpha times I equal to beta. So what is this? This is again alpha x is an I, and this is equal to beta, like this is equal to, this is equal to, and similarly this is equal to beta y, beta y plus beta. Okay? So you can easily check that this is an so these are again ideals. So alpha I, beta j are ideals in OD, right? So what kind of relation is this? Obviously, this relation is reflexive, symmetric, and also transitive, and hence an equivalence relation. Okay. So this is a reflexive, symmetric, and transitive relation, and hence an equivalence relation on the set of ideals. Why it is transitive? Because if I mean, you can easily see if alpha I equal to beta j and gamma I equal to beta j, then alpha gamma I equal to, sorry, gamma j equal to delta sum L, then alpha gamma I is beta comma j equal to uh, beta delta L. So I and L are clear, right? So it's clear that this is an equivalence relation. So let I denote an equivalence class. Okay, so next time we'll see that there's a group structure